Hi, Scott. You opened the room. Thank you.
Good morning.
Good
Oh, it's
morning.
not morning your time. Yeah, I
Could
didn't.
you do me a quick favor so I can set up everything?
Uh,
If you click on my profile picture,
uh,
on the bottom you should have an option to make me a moderator.
okay.
Because if you muted me instead.
Oh, gee.
It's fine.
S-
I'm sorry
I'm
that
following you.
that I.
Where's the moderator button?
So you click on my profile, and then
Yeah.
on the bottom there should be view full profile. Probably move to audience and then make moderator or something.
So I'm on
Should
the
be.
desktop
Uh,
program again, which just updated, but there's three
okay,
buttons.
on the desktop. Can you click on the desktop on my profile picture?
Yeah, I opened your profile. It says I'm following.
And then there's no button option, like
Wait,
make
on the
moderator.
bottom. There's three buttons. Let me see.
If
I'm
not, I'll
hovering.
just close. Could you close the room and then I'll open it up again? That would be maybe the.
Oh, okay, so just how do I close?
On the three buttons, leave.
Uh-huh.
There should be an option end room. Oh, I can end the room. Okay, I'll open it up again. It should be the same link,
Okay.
if that's okay. Okay.
Oh wait, wait. Oh, I see the button. Actually, it's right
Oh, you see?
next to your in the main screen. Make moderator. Are you sure?
Yeah.
Yes, I'm sure.
Perfect. Thank you.
Okay, good.
Okay. So, sorry again. And then don't be confused if you see now like notifications, people joined the room, people
Mhm.
have raising their hands. I'll take care of it, so
Okay,
don't worry about that.
sounds good.
And I'll put up the first thing I'm doing now is putting up your presentation, and then
Mhm. So the
we're working
so people
there.
click on it and load it on their device.
Yeah, do you see it now? There should be a link.
Yeah, Google Drive. Mm-hmm.
Yeah, exactly. So yeah, people can now click on it, and then we have still like 7 minutes or so. So
Yeah.
in the meantime, I'll add like topics and share on Twitter that we're starting, invite people. Hi everyone.
Great.
Feel free to share the room with people you think that might be interested. And thank you so much, Scott.
Yeah, that's great.
Um,
Thanks.
okay. So how's your day going?
Oh,
Everything?
good, good. Yeah, I was trying to get the time zone right. I'm in Mountain Time, so I'm like I didn't want to because I messed up our earlier meeting, but not I didn't want to mess up the seminar time. But yeah. And do they ask questions at the end or during?
It's really your choice.
Okay. Yeah, either way is fine.
So do you like those topics? It's pretty limited, the topics, like the assigned clean technology and engineering. I
Hmm.
can change them. There, there would be an option, probably climate change or something like that. But
Yeah. Trying to think what else. Maybe.
it's pretty limiting. Like
Yeah. There's not much
there's
there.
like, for example, no chemistry.
Yeah. Okay. I was gonna say chemistry. Uh, Hydrogen.
Yeah, there's no hydrogen.
Mhm.
So if you click on the topics, like you can check, like
Oh,
if you
okay.
click on the topics, then it pops up, um, and then you can search topics. Let's put hydrogen. No, chemistry is not, but there's like clean energy, like clean technology, climate change, climate, things like that. But
Mm-hmm. Oh, science and engineering is good to have.
okay. And I shared the paper in the chat, everyone. If people want to look at the paper, you should be able to access it. And yeah, and on top is the presentation. Feel free in the meantime to check it out. We will start in around 5 minutes, so yeah, will be a really interesting talk, and really looking forward to the discussion. I'm glad my cough is over.
Oh.
I had last week such a bad cough, like
Yeah,
I
I got
had
a
to
sore
mute
throat.
myself.
So. My voice is hanging in.
Yeah. Oh, you had the cold too? I think a
Yeah, I
lot
got
of.
a sore throat, but
Yeah, it was so embarrassing. I didn't know. It was so weird. When I spoke in Portuguese with my son in between, I was fine. But as soon as I started talking in English with the speaker,
that's funny.
I couldn't stop coughing. Maybe I forced my voice somehow in English. I don't know what.
Portuguese just flows better, I guess.
Yes, I don't know. It was really kind of because I would have cancelled if I realized how bad it was, but I didn't. Like, but gladly then a friend of like Serena, she joined and she took over.
Nice.
Yeah, hi,
She asked
Serena,
questions. Hi,
Scott.
Lars. How are you?
This I am. This is an excellent topic, and energy is an area of my interest.
Great.
It's an excellent topic.
Thank you. Yeah, hopefully it'll be interesting. First time I've given this
And
talk.
that's the future, especially now, talking
Yeah.
about the energy crisis.
Yeah.
Green hydrogen is the source of energy for the future.
Yeah, for sure.
Yeah, I agree. And we start in around 2 minutes. Usually people keep joining the 10 minutes after the official starting time. Usually people come in. So, but we have all the resources. The paper was shared on Twitter, so people had the opportunity to read up on it and join whenever they can join. It's always difficult to make a time that most people can join.
Right.
It's like really impossible because
Yeah.
we really have friends like in Asia, Europe, Australia. Like Katie is in Australia, and and here in the US, and everyone has different schedules. But that's
Yeah,
good about the recording. So.
Yeah, you archive it.
Yeah, and the cool thing, I don't know if I told you in the pre-meeting, the cool thing about the recordings here is that the links and the presentation and so on, they stay active. So if you replay it, it's really a replay on Clubhouse. The only thing you can do is ask questions, but other than that, it's pretty much the same experience. So that's why I kind of like this here. And yeah, no video. I hate the Zoom videos.
Yeah, I put a couple movies in and I was like, oh, it's not gonna work.
Oh yeah, if you have links to videos, I can share them if you would like.
It's fine. It's the movies are on with the paper, but that's not open access either. But it'll be fine with it.
Okay. And yeah, those type of videos, that is better, but I mean like having people on video. Like I don't know. I live in New York City. There's with 3 kids, there's really no spot where I have like a presentable No, it's fine.
Okay.
It sounds worse than it is. You know. Okay, I think we can start. Should I talk too much? Okay, welcome everyone to Science Society, and of course, a special welcome to you, Scott. And we are so grateful that you came here. You made the Clubhouse account and everything, went through all these hurdles to come here. It's a great honor. And before we start, let me give the audience a short introduction so that they can know a little bit about you. Dr. Scott Oliver is a professor of material chemistry at the University of California in Santa Cruz. And he did his bachelor and PhD at the University of Toronto. And there he worked on nanoporous and mesolamellar aluminous phosphates under the supervision of Professor Geoffrey Olsen. And after that, he went to Harvard University, where he was a postdoc, an NSERC postdoctoral fellow, and the lab of Professor George Whitesides, focusing on 3D mesoscale self-assembly. After that, he joined Binghamton University, I hope I said that right,
Yep.
as an assistant professor. And then in 2004, he went to UC Santa Cruz, where he's now having his own group, and where the lab focuses on developing materials that selectively remove pollutants from water. And other projects include nano and mesoporous catalyst, energetic material, plastics degradation, and hydrogen generation. And yeah, he published over 100 papers. His group is very interdisciplinary, and he uses a wide range of solid state and liquid-based characterization techniques. Yeah, as I said, it's a great honor having you here. And we usually start by asking a few interview questions, if that's okay with you.
Yeah, sounds good.
Perfect. So when you think back, like what drove you to go into science? Was it something you always wanted to do, like since a kid, or was there maybe a book or a class you took that kind of sparked the interest in becoming a scientist? Thank you.
Yeah, thank you very much, and thank you for the invite. I'd say it must have been high school because that's when science got interesting, and physics especially I found interesting, um, and chemistry, and so that. And I'm a kid of the '70s, so I grew up with astronomy books and Apollo model kit and stuff like that. So got me interested too. And then when I went to undergrad, physics just seemed like a killer series, and I chose chemistry, and yeah, I'm glad I did.
Yeah, that's interesting. That you I thought the same thing of physics. I was really interested in physics, but I was kind of scared.
Yeah, it was
So I went
intimidating.
into biology. um, but yeah, and then how did you come up to choose this field? Where your research is focused on now. Could you bring us
Yeah,
there? Thank you.
yeah. So when I got into chemistry, in my program in senior year, you choose which electives. It's all electives by then. This was at Toronto, so I chose. I mean, I always tell my classes that organic chemistry I found too much memorization, physical chemistry too abstract, but inorganic was just right. And some colleagues don't like that line, but anyway, yeah, so inorganic analytical chemistry is what interested me most. And then um, I joined the group at Toronto for my PhD on zeolites and nanoporous materials, and got really interested in that. So haven't left that area. But in terms of hydrogen generation, I got a story about that that I can relate.
Yeah, yeah, that's perfect. Yeah, what's
Yeah,
the story behind this project?
it
Thank you.
yeah. So it's pretty interesting that so I have an organic chemistry colleague who doesn't do the inorganic materials characterization type method. So his student actually discovered this process that I'm going to describe, and he was working. And don't do this at home for the audience. Like he was working at home. He's a chemistry major, not in a lab yet, and playing around with gallium and aluminum, and made this discovery. I mean, the reaction's been known for 50 years, but he found the ratio to be really important, and I'll talk about that. But anyway, in his kitchen, and so he got some gallium and aluminum, playing around with it. It's liquid in your hands; it melts, and um, went to wash, had some gray matter on his hands, and went to wash it off and got burned. So it caused this reaction that I'm going to show, and so that's how the discovery happened. He came into the building with bandages, and my colleague Bhaktan Singram, who's a co-corresponding author on the paper, said what happened and had him explain and said, okay, come in the lab and we'll study this, in a controlled environment. And they needed someone to help with the materials part, so that's how it came to be.
Yeah, that's interesting. So reach out to, you know, the student from us.
Yeah, yeah,
Also, and
it's how these kind of
yeah,
discoveries seem to be made sometimes. And it's Isai Lopez is a co-author. He's the second author on the paper. He's the one that discovered it.
yeah, and it's really great that yeah, that you guys supported the student in this way. It doesn't always happen, so
Right, right.
I think that's really wonderful, and yeah, that's a way to support young scientists,
Right.
which is, not always the case.
Yeah, they don't all get in labs. It's, yeah, harder all
Oh,
the time.
yeah, exactly. So, yeah, that's a really great story. Thank you. And yeah, now uh, everyone has access to the presentation on top. Please feel free to click on it. And Scott, the stage is yours. And don't worry about the chat or raising hands. I'll take care of it for you to read out any questions when they come up. And yeah, thank you.
Thank you. Yeah. So yeah, jump in anytime with questions as you feel warranted, and or we can do them all at the end. So I just clicked on my um, PDF, and so this format is interesting. I've kind of a read along uh, format like when I was young. So I'm on slide 1, and I've never numbered slides before, but I added those in for necessity. Um, so and then, oh yeah, I didn't put my university down here because this research is sort of spinning off. We have a patent um, that's about to be licensed to Green Hydrogen LLC. So I'm one of the co-founders of that company, and so I'm speaking from that perspective or angle here. Okay. Yeah. So I gave the background on how this came to be studied, and I'm going to jump to slide 2. So the sound effect. You remember old read-along books? Next slide. So slide 2, just an outline. Um, we use liquid metal as a reaction medium. Rather than doing reactions in gas phase or in a solution, the gallium is the reaction medium. And what you put in is an amphoteric metal, and I'll come back to that later. A metal that can undergo both an acidic or cause both an acidic and a basic reaction, such as aluminum. And I teach that topic in inorganic chemistry, so it's nice to see it come back here in this study. Um, and I'll show you it forms nanoparticles. It dissolves into the gallium. Gallium melts at about 30 Celsius, so you need a little bit of heat, even just holding it in your hand. And the aluminum goes in, and if you have the right ratio, you just add water, as the old expression is, and H2 comes off. So very rapidly, so within minutes, all the way, almost a quantitative stoichiometric amount. And what's nice about this is no CO2 involved whatsoever. The energy that we're making use of the aluminum zero, the aluminum metal that underwent electrolysis from aluminum oxide, and I'll get to this later. The energy that's stored in the aluminum can or foil, um, and it goes to back to aluminum three, and we use that energy, and that's what's causing this reaction. And so we don't need any heat input, well, just a tiny bit. We don't need any electrical source, no other materials, catalysts, no solar cell materials, lithium batteries, none of those. We don't need chemicals such as base or acid to change the pH. It's just you just put in water. I'll talk about different sources of water, and the reaction goes spontaneously with no CO2 involved at all. Going to slide 3. So just some background here on what's about half of the hydrogen is from steam reformation, so reforming of fossil fuels. So methane, this is a high pressure, high temperature reaction, requires catalysts, and you get H2 as well as carbon monoxide. So this is really endothermic, requires high temperature and pressure to do that. And the carbon monoxide undergoes further reaction to form CO2. So this is a lot of CO2 formed. It's kind of amazing that this is an energy source, a source of hydrogen. It's consumes so much power and produces so much CO2. But that's about half. And electrolysis comes to students' minds, but that's only a small percentage. It consumes a lot of electricity to split that water. Oxygen evolution reaction being the rate limiting step, releasing oxygen, and the hydrogen evolution to give hydrogen. You need electricity, and I'll go over that a little bit more later. So what we're doing is neither of those. We are doing a metal water reaction. So there's the overall reaction there. All of the aluminum becomes aluminum oxide, and all the water that is involved in the reaction. You do need some water. The oxygen, instead of splitting to make O2 gas, it goes onto aluminum to make aluminum oxide, as I'll show you. So for each gram, theoretically, we get over a liter of hydrogen for each gram of aluminum that's used. So going to, I'm so used to having a pointer too, but going to slide 4. Yes, that was slide 3. Slide 4, just an overview of the water splitting reaction. This is actual redox, and that is not what we're doing. Water you could think of as the H plus and O2 minus. So there is, in that sense, redox. But at any rate, this one forms oxygen, one oxygen, two hydrogens, water splitting, and you need a power source. It's, as you see on the redox potentials on the right, it is an electrolytic reaction. You need to supply electricity to get that to go. And the bottom left is just the reverse process. If once you have hydrogen, you can run that through a fuel cell and carry a load, whatever device or vehicle you're using, and out comes water. So water actually gets regenerated there. If you can capture that, there's your water. But at any rate, so yeah, that's slide 4. So slide 5 is just an overview of what we're doing. So we have liquid gallium in the center, and in principle, a given piece of gallium, be it small or large, can be used over and over again. So I mean, it's sort of like a loop, catalytic loop kind of diagram. And what we use is post-consumer aluminum. So, if we were to get aluminum from the usual process, yes, there'd be more energy put in to make that aluminum than we would get out from the hydrogen. So we use post-consumer, as I'll talk about, foil or cans or pans. and you just add water. Once it alloys, you just add water, and out comes and this is all that comes out: aluminum oxide, which is useful as well, and hydrogen gas. So you can use other metals. Mercury will do this as well. There's lots of YouTube videos out there, people playing with gallium, aluminum, mercury, aluminum. But there's a toxic aspect. Once mercury, it's metal is not toxic, but when it gets methylated, methyl dimethyl mercury by bacteria, that's extremely toxic. And other metals, if it's liquid, you could do this kind of thing, but they are not. Cesium and iridium is not stable in the presence of water. So that's just a general overall diagram. You know, in principle, you can go around this circle infinite times, but the key question is how much gallium do we lose in going around the circle, and I'll get to that coming up. Slide 6. So this is an overview of the process. Like I said, the reaction of aluminum and gallium has been known since the 60s, but what Isai did was, he, being a chemist, he played around with the ratio of the gallium and aluminum and found that even though it's the aluminum that's making the hydrogen, less of it is key to have. So you have gallium rich, you have more gallium than aluminum, and that led to a very efficient reaction for reasons I'll talk about shortly. So it's gallium rich alloy, and that was not studied in the literature or the patent literature or before. And we add in some post-consumer aluminum and manually mix, and that should be possible to automate that mechanically. Add any source of water, well, any. I'll show a few coming up. And then we just measure the H2 by displacement of water in a burette. Has the very basic setup that we had. Bucked on expertise in these kind of things. And then my expertise came in with the powder X-ray diffraction, scanning electron microscopy, tunneling, transmission electron microscopy, and so forth. And so we got very efficient hydrogen generation, very fast. In less than 15 minutes, it's mostly done, like on the order of 80-90%, and it sort of decelerates. And what's happening here is that you can't just cut up aluminum foil and use the aluminum, because of the native oxide layer from the oxygen in the atmosphere renders the aluminum inert to this reaction. So what's happening here is the aluminum dissolves into the gallium, and I'll show you, forms nanoparticles, and the gallium keeps the unoxide film from forming on those nanoparticles, allowing this reaction to go. Another point is we can make the alloy, and it is indefinitely stable. So we did several months, mix the alloy, and then just keep it under an organic solvent, such as kerosene, and then we used it after that amount of time. So indefinite. We don't know if it's unstable at all over time, like years. And there's the paper that Katerina posted. And I should say also, the movies didn't come through on the PDF. That was my miscalculation. But they are, if you have access to that journal, American Chemical Society, then we posted 5 movies with the paper that you can see. One of the clips I was going to show here. Okay, so slide 7. That was slide 6. Slide 7. Okay, so let's start on the right side. We went to the SEM, which has an EDX mapping addition to it. And so on the top right is just the SEM to begin with. You see these islands. And when you do the elemental map, so you're looking at the X-rays for just aluminum, you can tell that those blobular areas are indeed aluminum, and the rest of the medium is gallium. So that was what we were hoping to see, and the nanoparticles have some degree of polydispersity. They're not all the same size, but they are in the nano regime, meaning they're high surface area per gram, leading to a very efficient reaction. And so on the left is a bar graph where, so the first author in the paper is Gabriella Amberchan, and she's now teaching at Reed College. She tried, Bakhtan had her tried a whole bunch of different, as well as Isai. So Isai worked with Gabriella, grad student Gabriella, and you can see the results here. The best results were gallium-aluminum. GS would be Gallistan, so that's gallium indium tin alloy, quite expensive. That works, but not as well at different ratios. And then they also tried gallium, aluminum, indium, and so forth. So the best was gallium aluminum, and further, well, I got another plot on the next slide. Let's go to slide 8 with the purple, whatever color it looks like on your device, bars. So this shows the varying ratio of gallium to aluminum. So on the left, that was done already, 1 to 2, and further to the left, 1 to 3. So on the aluminum-rich side, there have been a lot of studies, even companies even trying to do hydrogen evolution at that kind of ratio. And it wasn't until SIE went to this gallium-rich side that it remains a liquid, an alloy, just above room temperature. And so they went and varied up to 3 to 1. There's a, as you go to the right here, it's more gallium rich, which means it's more expensive in that sense. There's you have more gallium than aluminum. You also have less hydrogen generation per amount of alloy. But so it's converse. It's kind of counterintuitive that you would get more hydrogen with less aluminum. But indeed, making that alloy is critical. 3 to 1 seemed to be the best with a drop off, although more studies remain to be done. 3 to 1 seemed to be the best, so that's what we used for all the rest of the studies. Okay, slide number 9 is the bluish turquoise type bars, showing you how much hydrogen's coming off based on the amount of aluminum in there. 100% would be, getting as much hydrogen as you expected. So it's not 100, but it's up way up there, and you can just use tap water. So it does not have. It can be distilled water, deionized water, but it does not have to be. And so that was good to see. And ocean water works, and we did GC mass spec to make sure we're not evolving chlorine gas. So that's why you can't take ocean water and just electrolyte, water split, because you get chlorine gas formation. So if you were desperate, and you didn't need that much hydrogen, or you had some efficient process, you could use ocean water, but the efficiency is much lower. And the reason for that is the chlorine likely forming aluminum chloride that's such a stable molecule. So we actually had some rain in Santa Cruz when we were doing this study. So they studied rainwater, all about the same. Commercial beverages, so vitamin water that comes to mind. They use Coca-Cola. So I would like to try beer myself. You got a can of beer. There's your energy source. There's your liquid source. And then going to the right side of this plot, recycled gallium. So you can use it over that, and that is critical. If it was a one shot, this would be dead in the water. It would be interesting, but not applicable. So they went back, used it again, and they've gone multiple times with that, and that is crucial to make this economically viable. Aluminum from food receptacle. That one, I believe that was the aluminum pan. I got another plot on the next slide. It was thicker aluminum. It didn't alloy as easily as a soda can. Oh, and then the last bar there is recycled water. So you can use the water over again as well. And, that does not, there does seem to be a little bit of a drop. So fresh, new water each time is advantageous. Okay. Slide 10, just some more plots. I just threw this in there because it shows you, you got a food wrapper. You've got you got cigarettes. Back when you could take the aluminum, burn off the paper. You've got a source of energy that we're all throwing in our recycling bins usually. But I should also say not all aluminum gets to recycling facilities. But that shows banana bread wrapping they used, and the baking tray, it was quite thick. So this aluminum, I should say, has to be ground up a little bit. So coffee grinder is what we used. If you take aluminum too far to a fine powder, it's very unstable, flammable. So you don't want to go too far on that grinding. The lid worked better than the bottom of thickness issue there, but the wall, the aluminum from the wall of the can didn't work as well, and that's just because of there's not as much aluminum there. You got more paint and more of the interior coating. Hopefully not BPA, but whatever the polymer material is there. So, and then on the green bars there, that just shows we live by the ocean, so they got some ocean water, and then just made artificial, similar concentration, got similar result. Oh, and there's Coca-Cola on the right. Okay. So Katerina, do we have any? I'm about halfway, so just want to make sure.
Yeah, I think you answered in the meantime most questions, like where to get the resources from. And
Mm-hmm.
one question is, what can kill the activity of the alloy or sulfur?
Kill the activity of the.
Yeah,
I missed that.
like what can interrupt, I guess, is the question,
Ah,
this reaction.
yeah. Um, the mixing to get the alloy, to get those nanoparticles is important. Um, so for like if you dump the water in too fast, things like that, the reaction goes violent and the aluminum will drop out too quickly. You want it to gradually just keep making that hydrogen and gradually go to the aluminum oxide. So, it's but if you see those movies, it is pretty it goes. But to get quantity, to you won't get as much hydrogen if you're not careful. Um, and yeah, the gallium doesn't have to be ultra pure, but a high purity helps for that. A little bit of that. And we've only done small scale. That's another thing. The movies that are with that paper is the scale that we've done. We've done the company is looking at scale up, and can't talk about that, but yeah. So thanks for that. So slide 11 is just some powder X-ray diffraction. So if you're not familiar, it's fingerprint method. You put your powder into the X-ray machine. You look at the diffraction peaks. You get a fingerprint and compare it to known data. And hopefully my voice won't go here. Okay. The green bars, the shaded regions, are so gallium is on the bottom from the database, the PDF powder diffraction file of the ICDD that sells the X-ray powder X-ray data. But you can go to papers, look up spectra, and you can see the pure gallium matches. So that's orthorhombic phase of gallium, and then with the alloy gallium rich, you see more peaks from gallium, then gradually up towards the top. Gallium to aluminum 1 to 4 is more aluminum rich, so not surprisingly, we see aluminum peaks for that mixture. So that's just some X-rays of the different alloys. And on the right is, well, the bottom three are reference patterns from the PDF, and the top is experimental X-ray after the reaction's done. And so what we see is aluminum oxide um, matching quite well to alumina or aluminum oxide. So that's just some X-ray I wanted to add in there. Slide 12. Oops. So when it gets PDF'd, you don't have a movie anymore. But that shows what happens on the movie is this is under cyclohexane, and the alloy's at the bottom, and they were dropping in aluminum. Sorry, they were dropping in. They made the alloy. It's on the bottom. Dropping water in the test tube, and it worked its way down the left side, and displaces the cyclohexane. And once it hit that bigger drop, the reaction had already started, but a big drop hits, and it just takes off. And it's a nice movie to see. So it's just a screenshot there. Slide 13, another movie. So on the top right, we've got the remote control car, toy car that Bachton bought. I think it was a couple $100. It's a hydrogen fueled remote control car. And so what you usually do is, there's another example on the bottom right. You have a solar cell. You have some water. The solar cell splits the water, makes hydrogen. The hydrogen feeds into the car. And so what they did is, instead of using that, they took some of the hydrogen from our lab, got it with difficulty into the valve, the gasket of the car, and got it to run. And then so there's a movie there that I can't show you. And Bachton, being an organic chemist, they love their organic reactions, and this one is kind of classic hydrogenation reaction that usually requires pressure, some atmospheres of hydrogen and heat. And Gabriella got the reaction to go at room temperature. She did all kinds of different substrates, all kinds of different reactants, and got that double bond to be reduced to a single bond. So we know we were making hydrogen, and it's useful as well. That reaction requires nickel acetate sodium borohydride to catalyze the reaction. But the paper has a lot of reactions involved. There's an organic flavor to it later on. Okay, slide 14. There have been theoretical studies of using aluminum clusters to do this kind of reaction. So this is what we believe is happening with the aluminum nanoparticles that are in the gallium. It's amphoteric. So, like the last bullet says, water converts to hydroxide at the Lewis acid sites, and hydrogen supplies hydrogen atoms at the Lewis base sites. So, the amphoteric nature of aluminum is being utilized here. And this group did molecular simulation calculations on that reaction in the presence of aluminum clusters. Now, and I should say, you can make aluminum clusters, aluminum nanoparticles, with much difficulty. You need expensive instrumentation and high temperature, to make aluminum nanoparticles. It has been done, but with our method, it's all room temp. So the so-called Grotthuss mechanism is what we believe is happening on our alloy. Slide 15. So I just went and did some back of the envelope calculations, as my inorganic professor would say. The top row is just giving an idea. That's what we published in yellow. So a gram of gallium, and the approximate cost, it's about $400 a kilogram for gallium at this point. That's what we published. And what the DOE talks about is a kilogram of hydrogen. How much does a kilogram of hydrogen cost? And from basic intro chem, calculate that to be 500 moles and of H2. And to fill up a hydrogen car, for example, it's on the order of 5 kilograms. So they want to know the cost per kilogram. And that's the amount of alumina that is formed on the right column, aluminum oxide, after the reaction's done. And so in orange, I highlighted, you can scale up a few times, and that's kind of the limit that our campus will let us use. So, we're chemists, but we're not allowed to use chemicals. I always say that to my students. But, large amounts of hydrogen, yeah, I could see, you need to be up to code, as our company is going to be doing. And so how many cycles would you need to make a kilogram of hydrogen? Well, from our paper, you'd have to do that reaction 70,000 times, which is unreasonable. In principle, you can go around that circle 70,000 times, but there are going to be trace losses of gallium just by the virtue of its solubility and things like that. So we get most of the gallium back. um, Now on the bottom row, I put it in red because you wouldn't want to do this. In one shot, you could take 65 kilograms of gallium, and I would love to ask Mr. Beast, do you want to try this reaction? That'd be fun. Um, in one go, just dump all that water in there and watch. But so there's a middle ground, which is what I highlighted in green. There's a sort of a common sense, reasonable middle ground where you have, not too much money worth of gallium to begin with. And in principle, once you buy that gallium, you can keep reusing it. About $100 of gallium, about half a pound, and you're going to make that much hydrogen. You'd have to cycle that many times, 273 times, to get to a kilogram of hydrogen. So even though 1 gram of gallium makes 1.25 liters of hydrogen, a kilogram of hydrogen at room, 1 atmosphere is like, I calculate, Hindenburg, like a tenth of the size of the Hindenburg, that kind of volume. So you need to pressurize it, just to have a tank of that's what they have in the hydrogen cars. And along the way, you're also getting, so I just plotted that. It's a straight line. You're also getting a lot of aluminum oxide that I want to talk about next. So slide 16, this using that green reasonable row in the middle, about $100 of gallium. That's how much hydrogen you're going to get out, and that's how much aluminum on the plot on the right. You're going to get that much alumina. Did I say aluminum? A very big difference. Alumina. You're going to be forming that, which is also useful. It's also a commodity product. So here's the overall reaction on the bottom left. Aluminum, water going to alumina and hydrogen. Yes, you need a fair amount of aluminum to begin with, and that's why we want to use exclusively post-consumer aluminum. Nevertheless, it's a room temperature reaction, well, just slightly above room temp. No additional pressure needed. You just mix these together. And just as a reminder, steam reforming of methane, there's the reactions for that. You get a lot of CO2 coming out overall. And this doesn't actually do it justice. There's catalysts that are needed, tens of atmospheres of pressure. 900 Celsius is typical. Yeah, so I would say nobody's been able to make hydrogen the way we have, at this room temperature conditions. Okay, slide 17, I just want to emphasize that there's many uses of alumina. Now, aluminum in the first place, abundant, with a high natural abundance, very safe, as long as you don't go too fine of a powder, and efficiency. So each gram, it's a nice ideal gas equation calculation there that SIE did, and I can't. I teach intro chem sometimes. I've taught it a couple times. If I ever teach it again, I'll put something like that on there for them. But anyways, at any rate, and then alumina, the aluminum oxide, is very useful. There's many uses for aluminum oxide, such as catalysis, doing organic conversions, or trapping H2S gas into a solid sulfur. That's a big use of aluminum oxide. Many more uses. Removing water from gas streams. It's used in all kinds of industries. So they buy aluminum oxide. So we have a possible commodity product from our, that's all we get. We get hydrogen, we get alumina, and the gallium comes back. I just put some other examples of applications there at the bottom. Okay. So basically what we've, in principle, if this can be scaled up to where we want, we've kind of made this process partially unnecessary. Bayer process is extremely, polluting, energy consuming. You mine bauxite out of the ground, which is a mixture of metal oxides. About half of it is aluminum oxide, and you solubilize it with base, so that's the cost there. And you filter, and out comes red mud. I got a slide of that on the next slide. you get, you solubilize it and then you crystallize it with seeds. This whole process, multi-step mining, is, when you think of mining, it's inherently polluting. So on slide 19, I just got a picture. I put a picture of red mud, um, the pollution that comes out of that Bayer process. And for each ton of aluminum oxide that you get in the end, you get 1.5 tons of this stuff. And the red is from the iron oxide, and it's also high alkalinity, which is not environmentally friendly either. So it's incredibly polluting. So we could provide aluminum oxide, without having to do all that mining. And then there's the last couple slides here. I'll just mention on slide 20, the getting from alumina to aluminum is energy consuming. Um, it's high temperature. It requires electricity, so much so that there's a photo. There's a plant in India that has a nuclear power plant right there to supply the electricity. It's staggering how much energy that takes to get to aluminum metal. And then I just put in, this is CO2 releasing. Fluorocarbons come out as well. Although not if you have a nuclear power plant to run that, but uranium mining is a whole other polluting process. But that gives you the market, 41 million tons per year. If you did that, all that requires almost a tera, uh, towards a trillion kilowatt hours each year to do that. So post-consumer aluminum is what we like to use. And then slide 21 shows just the uses of hydrogen. The pressure, like it was before the seminar started, that there's a lot of that is the future. Um, getting clean sources. So people want to use solar cells, but that is also um, environmentally damaging and has limited lifetime. But the hydrogen applications are shown on the right. It's quite staggering. The amount of news articles coming out now and plans by companies to make vehicle lines, trucks, trains, hydrogen trains prototype is big, and coming up later in this decade. And so there's a lot of pressure from above, especially in California, and then many states have locked their actions to California, be that good or bad. Will follow the same action to go hydrogen. So, and one thing about the uses of hydrogen, one of the big ones is ammonia. So the Born-Haber process to make ammonia for fertilizer to get enough food. So, that's also a late 1800s process and still in use today. But nitrogen comes from the air, but you need hydrogen for that. And with the so-called nitrogen caps we're seeing on food production, it's quite this is going to, the pressure to make more hydrogen is just going to keep increasing. Slide 22, I just put in, there's different colors of hydrogen, from gray, straight from um, fossil fuel, or from methane rather, for gray hydrogen. You can also make it from fossil fuel, and that's part of the puzzle. If you capture the CO2 coming off that so-called blue hydrogen, uh, and green hydrogen is so not zero carbon, it's low carbon. So I would say our process, if you have the aluminum, it is zero carbon. So I just wanted to make that point. And then finally, just a summary slide, slide 23. Don't take these numbers too seriously. I just quickly did searches on USGS and places, but on the bottom center is our circle that we go around, and reuse the gallium. Yeah, actually 99.99% gallium is only $200 a kilogram. The more nines, the higher the price. And we can use that type of purity. And on the right shows, all that comes out from this is gallium, goes back in. Hydrogen, we could, have trucks pick up. Same with the alumina. But in terms of the hydrogen, what we're looking at, green hydrogen, is on demand, you know, generation hydrogen where it's needed, at a filling station, for example, for hydrogen cars, at the scale that's needed. So industry needs more hydrogen, they have larger units, that kind of thing. So no transportation needed. We would just set up our, our modules, our reaction on site. Um, oh, and yeah, alumina is also highly useful. With higher, more nines there, the more pure it is, the more possible price you can get out of it, in principle. And then just one last thing, the Hall-Héroult process to go from aluminum to aluminum, the other direction is thermite reaction. So, for example, melting iron, like make railroads, for example. Anyway, I think I'll stop there. I went past my planned half hour, but as usual.
Well, thank you, Scott, so much for this presentation and for explaining this um, reaction and where to get the resources from and what the costs are.
Yep.
That's really, you covered really everything. It's so amazing. And you mentioned that you created a company to scale this reaction up. So, do you think by scaling that the price will go down? And what would be the ideal situation to scale this up? Like, what would you need, and
Yeah,
where would you start?
yeah, we might. It might not need like economy of scale type of thing, like because the reaction just goes that if the alumina can be sold for a good price, then that could drive the whole thing. Um, in that hydrogen DOE has this hydrogen shot, $1 a kilogram. We might be able to reach that. The other On the other hand, if we start using a lot of aluminum, then that'll go up in price. Gallium could go up in price, but we're hopeful that we have seen no limit on scalability yet. So um, yeah, we'll see. It's going to be interesting.
Yeah, and where, so you can get aluminum from different sources, right? Even recycled one,
Mm-hmm.
would that be
Yep.
possible? Yes, right.
Yep.
So that's a really ideal situation, I think, because aluminum to like mine the raw materials is kind of bad for health. I know, in Jamaica, there is traditionally a lot of mining, but the dust is really bad for the health of people, and there's
Yep.
not too much left anymore. So I think that's a really important part for using your technology. And how fast do you think you will be able to, give this to the world to use, basically?
Yeah, we're hoping to get get a site up and running in the next 2023, and there'll be a lot of research, and you know I definitely want Isai to be part of that. He finished his bachelor degree, so we're going to be hiring hopefully if our investors come through, and then I'm sure it would take a full year to get towards that, but possibly 2024. But yeah.
And do you see the market to be more in the US or more in Europe? I kind of see more pressure in Europe, and
Hmm.
here I have the
Yeah.
feeling, I don't know enough, but that EVs, people are pretty happy with EVs, but in Europe people want to use hydrogen fuel for cars. Like, is
Yeah.
there a difference, and are you maybe thinking of starting in Europe or here or?
Yes, yeah, absolutely. So, if once we get it working on a large scale, then yeah, we could go anywhere. And you're right, the pressure and it's pretty amazing. Like most of the news articles that we share with each other is coming out of Europe, and even our IP person was in Santa Cruz. There was a company from France with hydrogen powered bikes, and so they had a hybrid, half lithium battery, half hydrogen. Next year they're going to release only hydrogen. So you have this cartridge and it goes 100 kilometers. Now that you have to assist your bike, but it's yeah, there's future there too. Europe for sure is and they're under an energy crisis literally. So it's more pressure there, like you said.
Isn't how flight started more like, Hindenburg? I know everyone knows probably about that, but
Yeah.
like, wasn't the beginning of like flying large scale freights like
Oh yeah. Yeah.
with hydrogen? And I think
Yeah.
they are still in Germany, and so I think in East Germany, place where they built the big balloons I think,
Yeah. No,
to
totally.
transport.
It's really amazing. Like it's too bad about the Hindenburg. You know, I always think of that and Led Zeppelin one cover. Like it's it comes to mind because but it's there were problems with that ship apparently in terms of spark. I don't know. I'm like I said, I'm from the '70s, so I saw the movie in the '70s. But uh, total fiction. But helium is not viable because it's running out. So and hydrogen's even lighter. So you could use, in principle, you could use the hydrogen as the energy source and delivery mechanism. So it's something I hadn't realized till recently that okay, you could deliver instead of the when we it's really expensive to move natural gas and oil overseas. They're starting to do that like with Germany's crisis. But with a balloon, you could have goods shipped as well as the energy um, at the same time. So I think there's future there.
Yeah, I think that's the really promising part of it also, because I feel like we need to get away from all these trucks,
Yeah.
maybe. Well,
Hmm.
it depends on what the trucks run. I mean, there's already infrastructure for the trucks, so
Right.
kind of,
They do
but
have hydrogen trucks now. The prototypes I've
yeah,
seen.
yeah. So probably we need it everywhere.
Yeah.
And yeah, Jamie's joined the stage. Jamie, did you have a question?
Yes, thank you, Katerina. Hi, Dr. Green. Thank you so much for the talk. This is incredibly interesting, and your the work is really, really exciting and remarkable here. Um, I was wondering, am I understanding this right? And this is saying that it's actually you're able to take substances that are actually quite prevalent around the world and even in our homes and turn this into this renewable energy source so that we maybe have maybe even a separate recycle bin to put aluminium things in that can go straight to some kind of place to have them transferred to this fuel source that you're talking about. Is that something
Yeah.
that could be possible?
Totally. Yeah. Instead of instead of putting your aluminum in the recycling and then it gets hauled off, you just use it in your house to feed this reaction and you get energy back. Of course, then you'd have the aluminum oxide to ship off, but at least you have, instead of just tossing the aluminum, you get energy out of it.
That's incredibly exciting. And do you think that this is this going to be in the? Are you envisioning this becoming new different types of batteries? Like, would I buy a packet of six of these hydrogen things, or is it like something that would be fitted into something when you buy it and then charged later on? How would that work? Or
Yeah,
is this? Am I taking it too engineering either?
yeah, we're sort of picturing like a sort of a closed box with our alloy in there, and then you just feed in water. And so once it's spent, you could send it back. That's one model, and then we could sell cartridges with the alloy and that type of thing, at least on the small scale. Um, yeah, it's kind of interesting. Like when they talk about fuel cell, methanol fuel cell. I remember years ago when I teach materials chemistry, they were talking about capsules of methanol that you put for your phone. When you run out, or you buy some extra capsules. It's kind of like that, but yeah.
Is Does this mean then that we might actually potentially see cars that can jokingly like run on water? Then, like we've got the hydrogen cell and we just pour in something from the tap or something, and boom, that's us filled up for the day. That'd be incredible.
In principle, yeah. I mean, you could. Like someone asked about deactivation, like the agitation of driving might not be good. So we what we're picturing, is fill up stations. So we would like a gas station, but instead hydrogen, and people would fill up their hydrogen car, their tanks would get filled, which already exists. That California has a network of hydrogen stations, and I saw a map recently. The UK there's one in Northern Ireland, and then there's like a few in Scotland, and a bunch around London, kind of thing. But
That's amazing. And one last question then, because this is sounding like the kind of thing that the world is screaming out for at the moment, right? Because that would be able allow us to detach from so many, many things that it would take another room to go through all of the things that it would save us from. But I only asked this because you mentioned you're starting up a company, getting involved with this, and that's great. I'm totally supporting that. Do you have any particular position to make sure that like another massive company doesn't come and buy it and either shut it down or lock it up or make it sourcely from them so that they can charge exorbitant prices? Do you have anything in plan to try and make sure that it's able to be spread around
yeah,
at
so
all?
that's kind of top on our mind. We got to move fast, and we have IP protection in the U.S. So we have patent pending in the U.S., and so there's that part. And then we're gonna, as we build up more IP, we'll be going after world protection. But uh, and my partners say that doesn't protect you necessarily. So we just have to move fast and get things going as quickly as possible. And we seem to have investors interested enough to be able to do that, and hire people in and get things moving.
I'm very much rooting for you here, Doctor. I'm looking forward to seeing more about this. And please thank that student that suffered for science when he got burnt. I hope he's okay.
Thank you.
And
Yeah, it wasn't
thank
too
you.
bad. Thank you very much.
Good. And thank you very much for your time. Thanks.
Thank you.
Yeah, I agree with Jamie. um, and yeah, we all wish you, all the best because, those technologies are really important for our future. And also, thank you for working on this and, using your brains and everyone involved to do this type of projects. There are many people that, use their brain to work on Wall Street, but so it's
Yeah.
always it's always so I don't know, uplifting to hear that. So inviting speakers like you is not altruistic. It's like to not be depressed. No, but seriously, it's really uplifting to hear the progress you are making, and we will be following your work. Do you have time for one more question? Einar
Oh, yeah.
just joined the stage. Great.
Yep.
Einar, go ahead.
Yeah, hi everyone. Thank you very much. Quick question. So this is fascinating. But is it necessary to enhance the waste management when it comes to gallium? Thinking of the technology as mobile phones, etc., to
Yeah.
make it sustainable, or any thoughts around that? Thank
Yeah.
you.
Yeah. Thank you. Yeah. So I went to USGS has a good reports. What's it? Element reports summaries each year, and yeah, most of the gallium's from China, and but it's used so much in LEDs that it's more in Europe as usual, but there is like recycling efforts in the U.S. There's one in I think it's in Utah, but if that could be, you know, more effort put into that, then it might be possible to get the gallium back out of those devices. And yeah, it's because usually it's in trace amounts for like as a dopant um, for semiconductors. It need to be a large scale effort, but I think it's on the other. Was it 400,000 kilograms a year production of new gallium? So it's not that much per se, but fortunately we can reuse it. We just have to push that as far as we can.
Thank you very much. Yeah, cool. Thank you.
Thank you.
Yeah, we had the. How would the extraction work? I know we had the guest speaker here a while ago that talked about getting rare earth materials out of, devices with zapping them basically, so to kind of make it more efficient. Would that be a similar system?
I have
Or
not looked into what method they're using. Since I'm a chemist, I always think of solvents, nasty solvents, and I and I thought about at one point subliming gallium, but it melts so easily. But it turns out it's really hard to evaporate, so really high temperature evaporation. So that can't be it. But yeah, I'll look more into it. It's interesting.
yeah, he developed a new method that you basically don't need this high temperatures. You just zap them with, and then it's more energy efficient.
Yeah,
If you're interested, I can look up the paper. I don't,
yeah, that would be great.
have it right now, but yeah, that would maybe be interesting to
Yeah,
have like a full loop type of situation.
yeah,
It would be
right.
also cheaper, right, for you guys then if you have like your own cheap recycling
Oh
place.
yeah, for sure.
Then,
Some start the more demand there is for something, the more the price goes up.
unless we use the hydrogen to transport and mine it, then maybe it's not so bad.
Yeah, you could use balloons to get the gallium back from the mine.
Yeah. Well, Um, yeah, the hour is up. We went tiny bit over, but thank you so much for coming here. And we are, as Jamie said, all rooting for you and for your company that it flourishes and gets a lot of funding and starts up fast. We all need it. And yeah, please feel free to come back anytime. Maybe next year or so, you
Yeah,
have some updates. We would love to hear them. And yeah, we all wish you all the best. Thank you so much again.
thank you so much, and for all the questions.
Thank you.
Thank you.
Thank you.
Yeah, and thank you everyone for participating, being here, posting comments, asking questions. And we'll have next week rooms again. On Monday, we'll have Dr. Ed Boyden from MIT. If you don't know him, look him up. He is a really amazing developer of tools for neuroscience. So he will talk about his work, tools that image and control the brain. And then we have a room about epigenetics. It's really interesting how epigenetic marks are inherited also via sperm and in 2 generations. Till now, we kind of thought it's mostly egg related and so on. So, epigenetics is stuff that you don't change the genetic code, but you change stuff around the genetic code, so it's harder to read or easier to read. And it's kind of a more short term way of keeping environmental information in biology. So it's kind of really exciting. We have a deep about deep brain stimulation for depression. So yeah, check out the club, the schedule if you're interested in things like this. And Scott, thank you so much again. We really appreciate it and enjoy your soon to come weekend, everyone. Thank you.
Thank you again. It's great.
Okay, I close the room in 3, 2, 1. Bye, everyone. Thank you.
Bye.